Alrighty, so back to igneous rocks, and I'm not going to go through the slides, but bless you. When we last talked, it was mostly about the where and the how, crystallization, okay, and what that would result in, grain sizes or lack thereof. Now we're moving on to, if you enjoy this kind of stuff, arguably the cooler portion of it, because it is some neat stuff going on in the background here. But if you're chemistry phobic, such as I was, it might be a little yucky. I promise you, we don't get into the murky depths of chemistry that very much. You won't be, balancing equations, or heck, I don't even think you'd be writing equations. But there's just some general, understanding of how it all works out. Sort of helps the process go along, I think, in a lot of ways. So, I was just tinkering with this before class starts, so it will be just slightly out of order from your PowerPoint. Nothing too offensive, hopefully. So, while we, again, talked about the last time all these different chemistry, all these different textures, porphyritic, aphanitic, phaneritic, all that fun stuff. All right, and I said, let's just get by with coarse grain, fine grain. It's because I knew these other terms were coming. We have three chemistries listed. Sorry, I'm trying to find something. We have three chemistries listed here. All right, the felsic, the intermediate, and the mafic. And I tend to call them flavors. Three different kinds. I call them flavors because, well, they're made up of entirely different ingredients, for the most part, and the mineral content. And I think if we were to, a type of organism that ate rocks, if you would, they would probably taste quite differently. So these are three chemistries. And again, this mineral content is a little misleading because, remember, minerals have to be crystalline. And at the point we're talking, we are before crystallinity. We are at elements. Now, this is a horribly nasty-looking diagram, but I promise you it's not as bad as it looks. So, first of all, the top two rows are just names of rocks. Probably recognize granite at the very least. Maybe some of you recognize a few others. So we could ignore those for the time being. They also, by the way, they say coarse grain and fine grain. So something you know, something familiar. Then underneath that, well, those are your minerals. Again, some you recognize, some you don't. The funny thing is that some of these words you don't recognize. You actually do know the minerals. It's just that these chemistry, igneous rock people, so much in love with their chemistry that they use more formalized names than we do in Geology 101 or early geology classes. And I checked a few other textbooks. Some of them translate, some of them don't. So I've just always had you guys annotate. This is in your lab book as well. We'll talk about it briefly. Just annotate when necessary. Like potassium feldspar there. That's just albite. Okay. You guys know albite, or at least you will within the next week or two. Sodium-rich plagioclase is orthoclase. It's the pink one. Albite's the white one. Orthoclase is the pink one. You saw them in lab. Amphibole and pyroxene. Even I forget which one is which now, but one of them is hornblende and one of them is augite. Okay, they just use slightly different names. In lab, where it actually matters, we'll sort it out for you. I think pyroxene is augite and coal is hornblende, but nonetheless. Quartz, we recognize quartz, thank goodness, something else. Biotite, we know biotite. And olivine, we all know olivine, although unfortunately we don't worry about that very, very far side over there. But yeah, there is a rock that's more or less entirely olivine. In fact, you have it as your specimen of olivine. We just call it olivine for minerals. So the words are now translated, more or less. So what's up with these lines everywhere? Those lines correlate to this percentage diagram along the side. The idea being is that you could draw a single line down the middle of the granite rhyolite column, or the diorite andesite column, or the gabbro basalt column. A single line parallel through there, and it would represent any given rock, ideally a rock sitting in front of you in your lab. And then as it crosses all those wavy lines there, it turns into line segments. You follow? Like through biotite, as if you draw a line right through the B in biotite, straight up and down, okay? You're going to have a certain width. Let me do this with the mouse so the people at home can see. You're going to have a certain width of a line segment right there. And that width corresponds over here to a percentage. Let's say it's 15%. Doesn't really matter at this point, but you get what I'm saying? So your single line turns into line segments through biotite, orthoclase, albite, and quartz. And those values then equal 100. 100% is, total. And what that does is if you move it to the right or to the left, you can see how those line segments might be thicker in the pink area as the green area shrinks. Or as the green area gets bigger, vice versa, and so on and so forth. Actually, they both get bigger together. The white one, okay, the albite there. As pink and green get wider, your line segment through the white, the cream, would get smaller. You can't go over 100%. And it's a way of representing the different chemistries. We're going to skip these arrows for a minute and go look all the way down at the bottom here where you see silicic or felsic, intermediate, mafic, and ultramafic. Those are the three words we mentioned 5 minutes ago. Those are your three flavors of igneous rock. The one in your lab book, and the one that we'll refer to the most, has this at the top. So above granite and rhyolite, you'll see the word felsic. Granite and rhyolite are felsic igneous rocks. Above diorite and andesite, you'll see the word intermediate right off the bat. And because that's one of the things you need to know about the rocks, is that diorite and andesite are intermediate, and gabbro and basalt are mafic. Again, we don't worry about that far right column. We don't do ultramafics in lab. So let's mentally sort of throw that up there for a minute. And what we're actually saying then is that felsic, I don't like saying silicic. It sounds kind of dirty. I don't know. Felsic igneous rocks are made up of some combination of biotite, orthoclase, albite, and quartz. Skip over to mafic for a minute. Mafic igneous rocks are made up of some combination of olivine, augite, and a plagioclase that you don't actually know. It's kind of like the labradorite. Remember the one that flashed blue at you? It doesn't flash blue, but it's a real dark one like that was. All right, so mafic igneous rocks are made up of olivine, augite, and a dark feldspar. It's just a reference system. Intermediates then, they're kind of a mix. Weird thing about this pink band is that it sort of slowly but surely changes. It goes from white to gray to black, if you would. All these others are sort of unique kinds of minerals. The green one looks like it's not separated, but it is. But this center pink swoosh across the middle there, that's a blend. And again, chemically speaking, it's kind of important. Now, we'll see who's actually started at least mentally preparing for the test. Quartz, albite, orthoclase, in other words, the feldspars. Biotite, the micas. Augite, hornblende. Those are all what mineral group? Yeah. All right. They'll all show up in 1 through 12 in your mineral kits, which are all silicates. There's more silicates as you go through there, but those first dozen, all silicates. Yeah, so these are all silicates. So it's no surprise that we see this first yellow arrow here, increasing silica content as we go towards felsic, which is why they call it silicic. All right. But remember, with the exception of quartz, which is just Si and O, you got all that other crap in there. There's 14 weeks on this stupid diagram. All right, if you're sadistic enough, masochistic enough to take the class, I had to take it. It was interesting, to say the least. Far from my field. So they totally get into all this stuff. So increasing sodium and potassium, okay, as we go towards silicic, increasing calcium, iron, and magnesium as we go towards mafic. We're going to leave this idea for a minute, for 3. And remind you before we go any further what we're talking about. Talking about lava and magma, right? And this is that molten mineral mixture. A little alliteration for you there. It's really just elemental stew. We call it magma when it's inside the earth. We call it lava when it's at the surface of the earth. Same stuff. So what we were just spent however many minutes looking at here really represents pools of magma or lava. And again, these mineral names aren't actually here. There's SIs and Os floating all over the place because it's mostly SIs and Os. There's some Ks, there's some NAs, there's some calciums and irons and magnesiums floating around. But if they just threw all that crap up there, no one would know what the hell they were talking about, right? So they at least got to give you some mineral names to give you some basis, some founding. But in the back of your head, remember that you're actually seeing the formulas floating around, not the names. And again, we told you that there's 3 essential flavors, formulas, types that we're looking at. The felsic, the intermediate, the mafic. You dig? You with me? All right? Because some dude actually sat there and figured all this crap out. And this is another way of looking at it. Remember that band I told you that went across? All right, it's this gray one here. It's a plagioclase spectrum or something like that. You got your quartz again. You've got your orthoclase. You've got your albites. You've got your micas down at the bottom. You got a little hornblende thrown in at the very end. And remember, again, I don't even know why I have this diagram in here. Granodiorite and dacite. Good Lord, we don't even talk about those. Let alone peridotite and chromatite. Is that double I down there? Yes, it is. Chromatite. I guess we're going to go for it. All right. I apparently learned that back in like 93. I just don't remember it. So, anywho, you're going to see the granite rhyolite, diorite, andesite, gabbro basalt columns. That's what you're responsible for. I am never, ever, ever, ever going to hold up a hunk of rock right here in lecture and say, what is this? All right. But I am going to say, so you know basalt, right? And you're all going to go, huh? And you're going to know that basalt is that fine grain. That's one part, the first part of the lecture. Black rock, that's the second part of the lecture, because now you're going to learn that the mafic rocks are more or less all very dark colored because of their ingredients. So you need to know the rocks, but not like in lab where you have to say, oh, that's a hunk of, oh, that's a hunk of, oh, that's a hunk of. Because I'm going to say, oh, yeah, granite. You can smile and nod, but by the time it gets to the test, there hopefully is a little bit more behind that smile and that nod. Okay, so we still aren't talking about the guy that figured that all out yet. I think I want to reorganize these slides a little bit more. We're getting there. We're still in that molten elemental stew. Anybody here ever melt a rock? Probably not, right? Bonfires get pretty hot. Sometimes you might see like a tin can that almost sort of melted. But generally speaking, we don't approach temperatures that can melt rocks. But you can melt rocks. Granite, I apologize, this isn't in Fahrenheit, so we all could understand it. Granite melts at 625 degrees Celsius. Basalt, much more durable apparently, melts it over, greater than sign there, melts it over 1,000 degrees Celsius. Now, here's the thing. We're not actually interested in melting rocks, right? We were actually talking about making rocks a minute ago. As far as you guys know, rocks are hard. Rocks are solid. So why am I talking about melting? Well, let's talk about water. Water is really easy to understand. And one of the things you most commonly make go through its phase changes, right? Anytime you make ice or you make tea or cook pasta, you're putting water through its phase changes. So you know, for example, now that we all, most of us, have these little thermometers on our dashboards and you're out in January driving home and it's sort of raining, sort of snowing, you're like, and you look down and you see, okay, it's 31 degrees. What happens at 32 degrees? Water freezes, all right? I don't know about you guys, but I take great comfort in the fact that I know if it's 1 degree or 2 above that number that I should have a slightly less chance of slipping. Or if it's just below that, I got to drive that much more carefully because it's probably ice. So we take for granted that this liquid water turns into solid at a certain number, or the solid water turns back into liquid at a certain number. What else do we melt in? Well, butter, but nobody knows those temperatures, right? So we don't melt a whole lot of things in our lives. Chocolate, maybe. But again, you're probably not measuring that temperature. So water's all we got. So my point in telling you that basalt's at 1,000 for melting and granite was at what, 625? Something like that? Is because we understand melting. We want to crystallize basalt. Where do we need to go? Below that number. Yeah. All right. We want it to, if it melts at 1,000, let's just arguably say it starts to crystallize at 999. So on and so forth. So melting and crystallization are two sides of a very sharp knife blade. All right. You go just one edge to one side, you're doing this. You go one edge to the other side, you're doing that. So I introduce it as melting, again, because we get that. So, we're going to apply that in a minute. Told you there was a guy, right? Here's the guy. We'll call him Bob Bowen. lot of these people were Robert. I don't know if this guy was or wasn't, but Bohn's reaction series. Feel free, once you write it once, to just call it BRS or something like that. It's a lot to write in notes really quickly. So Mr. Bowen realized that there was a predictable sequence in which minerals would grow in a cooling magma or lava. What do you think he looked at, magma or lava? Yeah, probably lava. It'd be a heck of a lot easier at any rate, right? So you've heard of people sitting and watching grass grow. This guy sat and watched lava cool. Over and over and over again. Enough to realize that, and apparently different, types, so he had to travel the world too and gather different lavas. Kind of a cool job, really. And realize that sometimes different minerals grew if he had different lavas. I don't know if he had that idea already in his head. Think about it. Or he went and traveled, well, I better look at different volcanoes. Holy cow, how come this didn't grow in that other lava I looked at? And it came out that much. Again, this isn't my end of geology. So he may have already known there were different chemistries out there. Or that idea may have come out of this work. But either way, we arrived at those wonderful diagrams we saw a couple slides back. So not all minerals crystallize at the same temperature. There is a sequence. First this grows, then that grows, then the next thing grows. And what order do they do it in? It has to do with their melting point. Because think about this. The pool of magma or lava is hot. We are cooling it. We're trying to grow rocks. So we're starting at thousands of degrees and going down, so the things that would have melted last are growing or crystallizing first. So arguably you could have on your counter water, melted butter, and somehow lower the temperature in a controlled manner, and some chocolate. We'll put some melted chocolate next to that too. One of those is going to start to solidify before the other one, and then another one will solidify before the other one. And that should be related to what temperature they melted at. You follow? It's supposed to be two sides of the same coin. All right, we're going to skip over. There's discontinuous branch and continuous branch. I actually already introduced that idea. I've been meaning to delete this slide for a couple of years. We'll talk about it without using more vocabulary words. We're going to talk about the left side first. And we're just going to make up numbers. There's no numbers on here other than as you go from the top to the bottom, it decreases. And that's fine. We don't need to worry about numbers. So we're going to say 1,000 degrees. These, I happen to know these are mafic sort of minerals, and I remember basalt was at 1,000, so why not? Let's start there. Now, this pool of magma may have been at 1,500 or 2,000 degrees. Who knows? Nothing happens until you hit whatever the crystallization point of olivine is. Who remembers what's an olivine? Yeah, me neither. But there's a good chance there's some silicon, some oxygen. I think there's some iron in it. A couple of other things, right? It's that formula you wrote down that I told you you don't have to remember. You don't. But you do acknowledge that there's a formula, there is a makeup for olivine, right? Everyone gets that. If you want to make olivine, you need, just like making cookies, okay? You need this, you need that, you need the other thing. Okay, so as that olivine is growing, it's plucking silicon, oxygen, iron. We're going to say potassium. I don't think there's potassium in there, but I can't think of anything else at the moment. Potassium. It's plucking that out of the magma, sealing it up in a crystal called olivine. And it does that until it hits, let's say, 900 degrees. Again, just making up numbers here. At 900 degrees, it stops making olivine and starts to make augite, pyroxene, as it says on here. What's an augite? Who the hell remembers? But you do know there is a formula. So it's going to pluck the silicon, the oxygen, the iron, the magnesium, it's going to pull that out. So remember, you're using up your supplies out of your cupboard here. This is still that baking cookies analogy. All right? You're pulling that stuff out. Because let's say by the time you get to amphibole, there's something in amphibole that you ran out of when you were making pyroxene. Not going to be silicon or oxygen. Look what's at the very bottom here. Quartz is at the way bottom. You never run out of silicon and oxygen. Whatever's left in the end, it's just like making sugar cookies. Whatever's left, okay, well, we got sugar cookies. We got sugar and butter and, eggs. We're good. But you ran out of chocolate chips 4 hours ago. Okay? So anywho, you ran out of something that you need to make amphibole or hornblende. Well, guess what? It's just not going to make anything in that temperature. It's not like it'll continue making pyroxene. It stops at that temperature. We're down to what? 800 degrees now. I've been dropping 100 each notch, I think. So it doesn't actually make anything, which is great for biotite, and the potassium, remember, is orthoclase, because you're not using stuff up. So whatever there is in that mix, you can't run to the store and throw some stuff into your magma. It is what it is. So that's why, even though, you guys haven't looked at igneous rocks yet, but let's just say granite. Almost everyone here can picture a hunk of granite, okay? Picture a generic kitchen countertop, maybe a fancy building in some downtown area. You remember granite, pink, white, black, and sparkly, okay? That's why in a couple weeks when you get into lab and you look at a hunk of granite, the granite in group 1 is going to look a little different from the granite in group 2 and is going to look a little different from the granite in group 3. They're all granites, but because not every pool of magma is, even if it's felsic or mafic or whatever, there's still going to be different percentages. And you can't make exactly the same rock every time. Anywho, so the temperature goes down. We're now to what, 700 degrees? We start pulling out stuff for biotite. Same basic ingredients. Biotite, I'm pretty sure, has aluminum in it. Whatever what. Temperature goes down below. You see muscovite. We're going to ignore muscovite there. Potassium feldspar, plenty of orthoclase for you. Obviously some potassium and orthoclase, right? And then good old quartz. Quartz is the last thing to grow, to crystallize all the dregs out of the bottom. Remember those two words I told you not to worry about, discontinuous and continuous? Which one do you think this one is? Yes. Because we make something and we stop. We make something else and we stop. We make something else and we stop. We make something else and we stop. You don't need a vocabulary word for that. This one, on the other hand, see how it's all one smooth arrow? There's not those breakups. That's the continuous branch. This one, again, for folks that really enjoy this stuff, is kind of cool because there are a gajillion feldspars out there because they just blend. They very slowly but surely just grade into a different kind of mineral, but still a feldspar. We recognize the two extremes. All right, we recognize the light-colored, the albite. All right, remember bite teeth. It's going to be tooth-colored roughly. And then that one on the other end of the spectrum. The dark one I told you is kind of like labradorite, but it doesn't sparkle blue. We're still not giving you a name for that. Calcium rich. But what's in the middle? Well, we're going to kind of lie and teach you it's half and half. Because there is some half and half going on. There is some of that albite, there is some of that dark stuff, but there's also a whole bunch of weirdness in the middle that we just don't even recognize at this level. This, believe it or not, is that same table that we looked at for a while. If you take the silicic corner that's in the bottom right, and you flip it to the upper left. So it goes felsic, intermediate, mafic across the top like I've been trying to tell you it goes. This is actually that. I thought I put one in here. I went the wrong way. This is that table, which you're not seeing for some reason. That table. That table. So it was down here. We flipped it up. Trust me, it all tracks. That's where this table came from, at any rate. It was Bowen's work. Some of you are freaking out and imagining some horrific sort of matching diagram or something here. Okay, we're not going there. We're not going there. What you need to pull out of this were basically those two couple main ideas that I told you on a slide or two back. All right. There's a predictable sequence that minerals will grow. It's temperature based. And once you use something up, you might not be able to make anything else that needs it. All right, that's the foundations, at any rate, of growing igneous rocks. Felsic, the intermediate, the mafic, that'll all come in lab. Okay, I'm not going to say which of the following are felsic minerals. No. You'll learn that stuff. You'll learn to recognize that stuff in lab when we get there. And it doesn't actually take that long if you learn your minerals in the first place. Questions about Bowen's? Slightly less impressed than the person that said discontinuous branch earlier, because it's on the slide right there. But nonetheless, good job reading. I was staring at it for 10 minutes and didn't notice it was up there. Again, questions about Bowen's, what's important, what's not. Well, if as you're going through this stuff you start to come up with questions, you guys, you know how to find me. I'm sure your textbook will be much more clear than I was. Because now we're actually going to leave the chemistry behind and the grain size and whatnot. And we're going to talk about something that is related but doesn't really have a home anywhere else. Extrusive igneous rocks have a home. Extrusive igneous rocks are what volcanoes give us. Volcanics is extrusive activity. Lava. Well, what do you do with magma? Well, we get intrusive igneous rocks. And it's nowhere near enough for its own PowerPoint. Thank goodness. So we just kind of tack it on at the end here. Okay? So switching gears. This is narrative, don't even. So it said igneous intrusions, intrusive igneous rocks. There's some connection there, right? So the earth is old. She's cracked all over the place. Surface looks fairly uniform. We got that lovely layer of sediment and soil and whatnot on top. But underneath, it's fairly cracked up. And therefore, when a source of magma gets anywhere near the surface, gets anywhere near those cracks, just because of pressure, it will, kind of like caulking, okay? You squeeze on it and it goes into all those little cracks there. If that source of magma gets anywhere near that cracked crust, well, it starts to infiltrate and seeps through, if you would. Once it's there, it starts to cool off. Why? Well, because that cool rock around it is cool. You're farther away, from the heat source, the core, and from the mantle itself, which is, significantly warmer. And it takes a while, don't get me wrong. But, excuse me, but it does eventually cool off. I'll admit there are some times where the Earth breaks at right angles. But for the most part, just picture a crack or something shattering. It's hardly ever straight. Okay? It might wiggle out in one direction for a little bit, then fracture off in another way and split 3 ways and so on and so forth. And well, that is reality. We tend to generalize it a lot more, narrow it down a lot more, and talk about 2 things: dikes and sills. In our diagrams, we're going to use sedimentary rocks. There's a lot of sedimentary rock in the crust. There's more to it than that, though, but to keep things simple, we're going to use sedimentary rocks, which are traditionally layered horizontally, flat, if you would, like stack of paper, deck of cards, whatever. So when I say that dikes will be cutting through vertically and sills will be cutting through horizontally, or dikes will be perpendicular, sills will be parallel, whatever works for you, that is strictly in our diagrams and speaking of sedimentary rocks. It's all a relative thing. You got to look at the situation, look at the rocks that are there, look at how this cuts through, and then make the call. But for educational purposes here, we're going to make it as simple as we can. Now, you may be wondering why I said 2 things. You're used to me being a little whatever at this point. I do see the word pluton there. Pluton is just a fancy word for that pool of magma that we started with. All right, you do want to know that word, but it's not really an intrusion. So that pluton is the pool of magma. So dikes and sills. Dikes and sills. Big fancy word. I told you horizontal and vertical a couple minutes ago because that works for our diagrams. But I did tell you it was relative. Remember that? So that's where these 2 words come in. Discordant and concordant. What is discord? Any musicians in here? Psychology majors? What is discord? Like chaos? Okay, good. That's strong. Discord would be chaos would be a much stressier word than discord. Discord comes before chaos. But yeah, it's not a good thing, right, discord? All right, if you're in music class and everyone's playing along and you hear that kind of noise cut through, that's discord. It clashes with everything else, right? Well, concordant is the opposite. Con apparently means with. I never looked that one up, but if discord is against, concordant is surely with. So, going back to our examples where I told you we're going to have horizontally layered flat rocks, and I told you that a dike would cut through perpendicularly or vertically, and a sill would be parallel or horizontal. Sills, concordant, they're with the bedrock, that's with the layering. Dikes, discordant, that's cutting through the layering. Okay. So same thing now, just using the right proper words. They still keep these pretty straight and flat. My diagrams, as I said, tend to be fairly 90-degree kind of things. But as promised, even though you may not know what the different symbols in there mean. We'll learn rock symbols. Let's see if I've done this in order. We'd know the rock symbols by now, and I can quiz you real quick here. You're probably looking at the yellow is sandstone. Bricks are always limestone. That black stuff with the looks to be dashed lines through it is shale. Standard marine sequence. Now this is my image. Sand. Mud, shale is mud. And limestone only forms in salt water. So we see shoreline going back and forth over time in these rocks here. Regardless, they're more or less horizontal as promised. So if I were to point to this guy right here, which is one of the few unlabeled ones, would that be a dike or a sill? All right, hands up for dike. How many people think that's a dike? Again, many of you weren't looking, so we're doing this red one here. How many dikes? All right, how many sills? Okay. So sills go horizontally or vertically through sedimentary rock? Horizontally, all right. And we do have a couple sills right here, more or less being flat things. So this is indeed a dike, and we've got some more dikes over here. This one's actually labeled. You got another dike here. Do not worry about laccolith. We don't need that word. Now, what we need to think about then is how these actually manifest, how you actually see them if you were out in the field, if you were out walking around on the rocks. Igneous rock, you may or may not know, is fairly resistant stuff, especially compared to sedimentary, which we're looking at here. So weathering and erosion erasers, right? That igneous is going to stand there a lot longer before it breaks down than the sedimentary is. So you might actually see these dikes. This one goes to a volcano. Let's look at this one here. All right, you may actually see you're walking along sandstone, 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 and then you see this big sort of lump in the rock there where that's that granite bit of dike going through there. And remember, this is a 3D world, not a 2D diagram. So that's going to look sort of like a pipe almost, right? Whereas if we erased all this stuff and got to one of these sills, you would be walking on a big, flat, sort of granite, whatever kind of rock it is. So it's not the best, but see where it looks really wet there in the middle? All right. And there's a tiny little guy there pointing. Must be a geologist. No one else would stop. So you see that the rocks are going horizontally. We're in limestone or something here. Maybe sandstone. It's kind of hard to tell. But there's this big old whoosh right through the middle of it, cutting through it. It's a big old intrusive dike right there. All right. And if you got it close enough like he is, you'd notice that it is different rock type, so on and so forth. Mother Nature is not always that obvious. When it's nice, and when it does, it's nice, and we like to stop and take pictures. Here's our sill. Again, these couldn't be more textbook. Your layers are all horizontal here. And yeah, there are some dark spots there. Sandstone tends to weather funky, but that band is definitely some igneous pipe work being laid there. Sills do tend to spread out a lot more than the dikes do, primarily because you're going into there's an inherent weak spot in between layers of sediment anyhow. All right, let alone that there was a crack there in the first place. So like I said, these do tend to definitely think 3D about this one, that goes into the board, and in thousands of years in the future, if you were to wear down all that rock above it, you would have a horizontal surface essentially that you could walk across. Whereas this guy probably be much more pipe-like. So if there's enough pressure and enough magma, this pipeworks can work its way to the surface, break through, and we have ourselves a volcano, which is where this conversation would typically go to next. But as I said, we have to go back and do the rock cycle. So what this really illustrates, and again, I like to admit when I might not know what the heck I'm talking about, this really illustrates that there isn't a whole lot of difference between magma and lava other than their location. Okay? Because just in a moment, one can become the other. Now, the reason I said there might be something I don't know about is because there could be something to the fact that certain magmas are much more likely to make it all the way to the top. It's more than just volume and pressure. That possibility exists. That I just don't know about it. But I think, for now, for our purposes, we are fairly safe in saying that, hey, if it gets lucky enough, for lack of a better word, to make its way to the surface, party popper time. You get a volcano. And not all volcanic events are big pointy mountains. You'll learn that. Sometimes it just kind of leaks out and bleeds all over the place. All right, that's called a fissure eruption. And that gets its whole entire chapter all to itself. And like I said, volcanoes is long, lots of vocab. So be ready for that one.